Good morning, everyone. Last week we have started to discuss extrinsic semiconductor. So there's a case that what we call the degenerate and non-degenerate semiconductors. So when the concentration of electron in the conduction band exceeds the density of state, NC, so just like the band diagram showing here. So if once we have the conduction band, valence band, but if right now our concentration of electrons exceeds the density of state NC, so that means our Fermi energy right now will be above EC, and then so usually the Fermi energy will be in between, but right now we have the case that Fermi energy is above the EC, and in this case we call the degenerate N-type semiconductor. Also, on the other hand, we can also have the case about the degenerate P-type semiconductor. So in this case, our Fermi energy is below the EV, and that's what we call this as a degenerate P-type semiconductor. Since we start to talk about the extrinsic semiconductor, so we have to also try to evaluate the charge neutralities once we have the extrinsic doping here. So in this case, we assume there's a donor energy level just slightly below our conduction band, and ND is a concentration of the donor photons, and the ED is the energy level of the donor's photons here. And as we already discussed in the last week, that in this case, once the ionized, so once the ND is ionized, so that means part of this will start to contribute electrons here, and the positive charge will be left behind in this forbidden band gap here. So therefore, we can consider as a charge neutrality where your concentration of the donor photons here plus your positive charge left behind in the forbidden band gap will be equal to the ND here. So the small ND is a concentration of electrons in the donor energy state. The ND plus is a concentration of positive charge donor state. That's what we call the ionized donor. And these two will be equal to the concentration of the photons here. So for example, we can use a simple example to understand here. So for example, once this ionized, let's assume that we have the 9 electrons in above the conduction band, and therefore we have if we total have the 10 electrons of that's a concentration of the donor photons here. So therefore, we have 9 electrons will be jump to above the conduction band. So that means you have 1 electrons in the donor state. And also, because we have 9 electrons jump to the above the conduction band, so that means we have the 9 left positive charge will be left in this region here. So we will have the 9 positive charge. So that in this case, that's what we call the ND plus here. and this is ND, small ND. So therefore, you can understand this plus this will be equal to this one. So this is exactly why this expression will be shown like in this case here. And therefore, we can start to do some simple calculation, and we can have the ND, which is concentration of electrons in the donor state, will be equal to this minus this one. And also the ND plus is a concentration of a positive charge donor state, can be also calculated as shown in here. And since we have already previously discussed that when we consider the carrier, we have to use the statistics, and therefore we also have to use the statistics to describe the donors and acceptors here. And here is therefore we have to introduce a probability function. So the distribution function of the donor electrons in the donor energy state is then slightly different from the Fermi-Dirac functions here. And the ND is a concentration of the electrons in the donor energy state, and which ND can be expressed as shown here. And ND is also the one that we have shown in the previous slide. And sometimes we also have to consider the degeneracy factor here. So therefore, the 1/2 is actually come from the 1/G, where G is called the degeneracy factor. And P0 is a concentration for holes in the acceptor energy state. And therefore, the general expressions of this one is shown here, which is very similar to this case. This is just the case for the ND, and this is case for the NA. So with considering this one, we can start to do some simplified calculations. And then, for example, first we assume ED minus EF, which is larger than KT, and therefore this one can be rewritten as this seems. And also in the previous slide, we have been already talked about this is how the N0 will be equal to NC exponential EC minus EF over KT. And therefore we have this one in there can be calculated as shown in here. So the EC minus ED here is just a ionization energy of the donor electrons here. So now we can estimate the concentration of the ND over this is equilibrium case, which is matter with our ionization energy. So that's why in the last week we have to define the term of the ionization energy, because that's actually in the end will correlate how many electrons can contribute as how many donors can contribute as electrons here. So this equation is very consistent with what we discussed here. This is our ionization energy here. So in the last week we already talked about the concept that this is donor state, and as long as the donor state is close to the conduction band, that means lots of the donor state can contribute electrons here, because that's getting close to the conduction band. These things can be also understood by using this equation, because as long as this becomes smaller here, and that actually have a higher electrons concentration in the above the conduction band. So here is one example, just one example to give everyone an idea that how actually the ionization energy influence our ionization rate here. So determine the fraction of the total electrons still in the donor state. So where is the donor state? This is the donor state. So we are wondering that how many electrons still in the donor state. So if we consider the phosphorus dopant in the silicon at T equal to 300 K at a concentration of this one. So therefore, this is a concentration of the electron in the donor state over this term. And this is ionization energy here. So in the end, based on this ionization energy with 0.045 electron volts here, and that means we have only 0.41% of the electron in the donor state. So that means more than 99% of the electrons are already in the conduction band. So that's actually we can consider this is a completely ionization. So that's why in the silicon case, usually this is not a problem. In the silicon case, we didn't often to talk about the issues of this donor state, because that means whatever we dope in our semiconductor, it almost like more than 99% will contribute the electron, because the ionization energy is very small. So in this example shows that the very few electrons still in the donor state compared with the conduction band, because there's only 0.41% still in the donor state, and that means more than 99% of the electrons are already in the conduction band. And essentially all of the electrons for the donor state are in the conduction band. And since only 0.4% of donor state contains electrons, so we can say the donor state are completely ionized. So in this case, that are completely ionized here. So if we use these figures, that can also help us. So that means there's only 0.4% electrons still in the donor state, but more than 99% electrons in conduction band. So therefore, that's we can say this is a completely ionization. And since this is in the case of silicon, that's why most of most of the people, when they talk about when they're working in a silicon device, probably they can just ignore the issue of the ionization energy, because the ionization energy is very small, and that's almost equal to completely ionization. But if we talk about other materials like 2D, like a compound semiconductor, and that's a different scenario, because in the case, for example, in the case of a compound, and usually ionization energy is quite large, so that means you cannot consider that as a complete ionization. Sometimes the ionization rate is probably less than 10% in the compound semiconductor, like the gallium nitride or silicon carbide. Okay, so as we still have to consider the charge neutrality here, so we can use these charge neutralities to give us a certain more like the calculations. So the charge neutrality condition is used to determine the thermal equilibrium electron hole concentration as a function of an impurity doping concentration. So in the previous slide, we have already discussed the N0 plus Na minus, that's equal to P0 plus Nd plus here. Sorry, this is not a mention in the previous slide. This just show me here that these two actually will be due to this term will be equal due to the charge neutrality here. So N0 and P0 are the thermal equilibrium concentration of electron and holes in the conduction band and valence band here. So we have the conduction band, we have a valence band. And now we have to consider the case which both have the donor state and acceptor state. So we have the case of the donor state and acceptor state here. So now we all know that there's a part of the electrons in the donor state is able to ionize and jump to the conduction band. So therefore, part of this one can be ionized and become the electrons. And since there's some of the electrons jump to the conduction band, so that means some of the positive charge will be left at here. And this is what we call the ionized donors. And of course, there's some part of the is still existing because not like the 100% can be ionized. And there is some part of the region here because there's no ionized, so then all the charge still stay in the donor state. So this is unionized. And also we have to consider there's a thermal equilibrium electrons, which is not generated by this donor that's already existed there. And also this same concept can also be applied in the case for the holes as well. So we have the electrons left in the acceptor state, and some part of, not all of them are ionized here. But in general, this is called the ionized acceptor. And also, there's a part of a region that's unionized. And we also have the thermal hole. So that's a compensated semiconductor, shows ionized and unionized donor and acceptors. So the Nd is a concentration of electron in the donor's energy state, and Pa is a concentration of hole in the acceptor energy state. So therefore, ND plus is equal to ND minus here, and NA minus is equal to NA minus PA, and where the ND plus is a ionized donor and Na minus is ionized acceptor, and therefore with considering the charge neutralities shown in this one, and therefore the N0 plus Na minus, which is equal to this one. So this is the case once we both have the acceptor and donor state in the semiconductor, and then part of them is ionized and part of them is charge left in the inside the band gap, inside the donor or acceptor state. And since we have to consider for the further calculation, for sure that we will start to simplify the case. So right now we consider the case of a completely ionization. So that means these are both equal to 0. And the previous equation is now simplified as shown in here. And also we have already know from the previous class already know this equation. The N0 times P0 will be equal to Ni squared here. So then we can put it in here. And that's just a very simple equation, very easily to solve. And therefore right now we can have the answer, we have the solution for the N0, which will be equal to So that's an analytical equation to calculate the N0. And also doing the same things, we can calculate the P0. So finally, we have the equation that allows us to calculate the P0 and then the N0. So also there's some case that once we add additional donors here, so once we have the additional donors added here, actually there will be the redistribution of the electron when donors are added. So as you can see, because of due to the few donor electron will start to recombine with the intrinsic holes as shown in this graph. And now we have to move to understand that how do we determine the position of the Fermi energy. We have the expressions before, which is N0 is equal to NC exponential minus EC minus EF over KT. And with simple calculations, we can know the EC minus EF is equal to KT natural log NC over N0. And now if we assume this is the case when our ND is larger than NI, and also when our N0 is equal to ND, then we can have the equation shown me here. So that means actually our Fermi energy, position of our Fermi energy and we have the EC and EV, and then in the middle we have the EFI. And above the EFI we have the EF. So that means the difference, first of the EC minus EF, that's the difference of here. That's mainly determined by your NC over N0. And now if you consider difference between EF and EFI, and that's become the difference between the thermal equilibrium concentration, that's the N0, over the intrinsic carrier concentration, that's the Ni. And similar things can also be found for the case of the P0, and also in the case of the Fermi energy with respect to the valence band. So similar, we have the EFI in the middle, and we have the EF that's close to our valence band, and therefore the EF minus EV, so the EF minus EV just related to our natural log NV over P0, and also the EFI minus EF is equal to KT natural log P0 over Ni. So in the end, although we spent quite a lot of time to derive the equation from very beginning to introduce the concept of the band diagram and so on until right now, but the conclusion is always very simple. The equation here is although of course it's not necessary to memorize, but at least the main physics concept is that your Fermi energies will determine by your concentration. So if you look at this curve, if our EF is close to EV, so that means this is smaller. And if this is smaller, so that means this is larger. So that still quite makes sense because of the from the Venn diagram concepts already tell us that once you close to a valence band, you should have the very high Hall electrons. And these things can be also characterized by using this equation that as long as this getting smaller here, this term is become larger. So now I think that everything is very consistent. Sometimes you can easily to understand using the Venn diagram with the plot that already have the physics inside. Or sometimes we can use this analytical equation to further prove that our understanding. So as the doping level increase, the Fermi energy move close to the conduction band for the N-type. So this is the Fermi energy move close to a conduction band for the N-type material, or close to the valence band for the P-type material. So these things just already mentioned here. As long as our concentration is increased, EF is moving close to a conduction band. And as long as our concentration is increased in the P-type, our EF is moving toward the valence band. And this just the graph to summarize what I just mentioned. This is low concentration, this is a high concentration. So once you increase the concentration and your EF is getting close to your conduction band. And this is for P-type. Once you increase concentration and therefore your EF is moving toward the valence band. So the upper axis is for the ND, and then the bottom axis is for the NV. And also there's a additional, like you have to concept to know that the intrinsic carrier concentration Ni is also a strong function of the temperature. So EF is also the function of the temperature. Also, so as the temperature increase, Ni increase, and EF move closer to the intrinsic Fermi energy here. So you can see that this is 100K, this is 300K, this is 500K, and this is EF. So once you increase the temperature, actually that will be close to your intrinsic Fermi level. At the high temperature, the semiconductor material becomes to lose its intrinsic characteristic and begin to behave like intrinsic semiconductor. So you can see this is a temperature, this is electron density versus a temperature. Since this temperature here is 1000 over T, so that means this is a high temperature, this is a low temperature. And usually we prefer to have the region to have the extrinsic, because we can use the doping to modulate our concentration. We can add the N-type, P-type to increase or decrease of the certain concentration, either for P-type material or N-type material. But once we move to the high temperature, everything will be toward as an intrinsic concentration. And in this case, we lose the capability to control the doping, because whatever you try to dope, no matter for the acceptor or donor, it always doesn't matter. You always have the concentration approach to the intrinsic semiconductor. So this actually is something that we don't want, because as being cool for the semiconductor material is that we can dope extrinsic material to modulate the concentration, to modulate the electrical characteristic. But however, if we put our semiconductor material in a high temperature, everything will become similar to the intrinsic, and this is something that we don't want, because we lose control capability of to change the material properties or the electrical characteristic. And also one more thing, there's a region what we call the freeze out. So at a very low temperature, freeze out occurs. So this is because of at a very low temperature energy, actually your donor atoms or acceptor atoms cannot be ionized, cannot contribute electron and holes here. So you will still see at this region, we are no longer to have the completely ionization. We are actually having the partial ionization here. And this is the case for the extremely low temperature. And what's actually the environment that we have to consider in these two extreme cases here. So of course, in our daily life for our consumer electronics, we are always operating in this range. That's a typical like environment for the human beings here. And in the case for the high temperature, that's only for the very unique environment. And usually probably will be in the certain space, in the space region, we need to have a semiconductor that can operate in this temperature range that we already discussed before, that why that the NASA they want to use silicon carbide, because silicon carbide has a certain advantage using in this high temperature environment. And on the other hand, what would be the condition, the environment that we need to consider for the electronics application? And nowadays, this is an issue mainly for the quantum computing. So I think no matter you understand the quantum computing, quantum device or not, you must already heard about this term about the quantum. So in the case of quantum computing, we usually have to operate our semiconductor device below like 20K, sometimes below 4K, even below 1K, because due to in that extreme condition, the material can exhibit a very special, unique property that we can use for the quantum computing. But in this case, our semiconductor material has to operate in such low temperature environment, and such low temperature environment, we have the issue of the partial ionization. So that means whatever we dope in the donor state or whatever we dope in the acceptor state, we cannot guarantee 100% of these donor atoms can contribute the electron. We cannot guarantee the 100% of the acceptor atoms can contribute the holes. So that's the issue for the quantum computing. Okay, so here's a summary. In this chapter, we talk about lots of the analytical equation, how to derive. One thing, the reason why we need to derive this equation, because we want to further to support our physics-based understanding, support the understanding of the Venn diagram, support all of our physical gates. But now we have the strong evidence come from this equation, and this equation gives us a sense of the same conclusion like what we already know from the physics understanding. Another thing is, because this equation is also important for the exam, for the evaluation, because in the midterm, no matter for the midterm or the homework or final exam, you definitely need to use this equation to calculate some numbers here. So therefore, you still have to get used to all this equation. Of course, you don't have to memorize in the midterm. We will provide the important equation that's already enough for you to further calculate it. And in the final exam, this open book exam, so you don't have to bring everything. You don't have to memorize everything. You can bring everything, whatever the textbook, whatever the slide, even you can bring the computer. But the interesting thing is that the final exam is an open book exam, and the midterm exam is a closed book exam. But the average score for final exam is always lower than the midterm. I don't know why, because it's interesting. It's open book. You are welcome to bring everything. There's no limitation. Some of you already follow my class in the last semester, so you know my style in the final exam. You can bring whatever you want. But that's weird that usually in the end, the final exam has a lower average score compared to the closed book exam. Okay, so here is a summary. Using the concept of the complete ionization and charge neutrality equation for the electron and hole concentration as a function of the impurity doping concentration was derived in this chapter. So we can finally calculate the position of Fermi energy as a function of impurity doping concentration. And these are the very important equation, because in the later, no matter for homework, midterm, final, you always have to use this equation. And some of you are the undergraduate student, might be in the future. You know, in our system, we have the two ways of the graduation entrance exam. One is by using your undergraduate project, and you go for interview. Another one is you have to prepare for the exam. And this also if you target for the exam test for the graduation graduate school entrance, then these all the equations that you have to very familiar with. Okay, so we will move to the next for the carrier transport. So in the previous, we have been discussed a lot about how do we calculate the concentration for the carrier distribution. We need to apply some statistics, and we also have to consider the Fermi energy, consider Venn diagram. But there's still another set of the basic knowledge we haven't talked about, is about how this carrier transport. In the previous chapter is mainly to calculate the concentration of carrier. So we want to understand that how many electrons in the piece of material, how many holes in the piece of material, and why, for example, how do we specific understand the key parameters that will influence our concentration. But this is in the case that we don't expect this carrier can move. But now we have to consider the case that actually the carriers can be moved. And in this situation, we have to understand the carrier transport. The carrier transport, the understanding of carrier transport is very similar. It's very simple. It's just like the general physics or high school physics. You already have a little bit like a basic sense about this transport. Is mainly related to, for example, we have the drift, we have the diffusion. So diffusion is mainly the concept comes from the chemistry. So you have there's a region where you have a high concentration, and it must be this high concentration will start to redistribute to the other region that has a low concentration. So that's a concept of the diffusion. And the drift is a concept related that once we apply the additional electrical field, and the carrier can start to move based on this field. That's the drift. So this summary that what we are going to talk about. So it's everything related to how this carrier transport. So first of all, we still have to understand that even we don't apply any field and there's no concentration difference, there's already the move. That's what we call the thermal motions. So even without an applied electric field, carriers are not at rest, but possess finite kinetic energy here. So once the carrier has energy, for sure that it will not just sit there. So it definitely will start to move. So electron and holes move at the thermal velocity. But not in a simple straight line fashion. So that means in the case without additional field or additional concentration difference, the electron and holes can be moved, but it's moving like in this way. That's what we call the zigzag motion. It's due to the, for example, collision or scattering. This is because of, for example, we have some imperfections in the crystal, so that will cause this carrier has a collision or scattering. But the net thermal velocity is 0. So in general, that still looks like it doesn't move because of the net velocity is 0. And the mean time between the collision is around this time order. And now, for sure that the one we are interested in is that once we have some external force. So for example, the one external force can be the electric field. So this is a mechanism that we call the drift. So the drift is a motion caused by an electrical field. And clearly, drift is usually at the plane when voltage are applied to the semiconductor device. So that means once we apply the field, then we can start to see this one will start to moving toward the right. This is because once we apply the field here. So when voltage are applied to the semiconductor device, and then since we start to apply the field, then you will start to see the electron and holes move. So we can start to think about how to calculate the moving rate. So that's we call as a mobility. So we want to understand how fast this carrier can be moved. So once we consider the carrier drift, the drift momentum gain between collision is equal to the force Q times the mean free time. So it's showing here, this is momentum, and this is our force times our mean free time here. And therefore, we can consider the V, which will be equal to this one, and our mu p is equal to q so this is mu p, so that's describe p for sure. This indicate this is a case for the Hall, and mu p is Hall mobility. So this is case for the Hall mobility, and the tau mp here, this is mean free time. And also the mp is effective mass. So similar, we can calculate something for the electron mobility as shown here. So we have a mu n so still the same. This is n indicate this is a case of the electrons, and this is a case for the electron mobility. And also this is a mean free time, and this is a effective mass. So that's the general definition for the mobility. So if you look closer for this mobility equation, then you can find out that this is related to effective mass. So effective mass, this kind of concept we also have been mentioned in the previous lectures here. So that's mainly the things only related to the material property. So it's not it's a constant that cannot be changed. And if you use a different semiconductor material, you have a different effective mass. And this mean free time is also kind of a constant. So then we can realize that the mobility here is also a constant that highly depends on the semiconductor material. So if you change a material from silicon to germanium to gallium arsenide to the other like indium phosphide to the gallium nitride or silicon carbide, each semiconductor material has its own effective mass and has its unique mean free time. So therefore the mobility can also will be huge difference here, and that's usually considered as a constant that's highly related to the material properties. Okay, so once we have this basic, we can start to do some like the further calculation here. The first one is we are interested in for the drift current. So the drift current, this is a drift current for the holes, and this is for the holes, this is for the electron. That's mainly related to your concentration for the holes times your velocity, and your drift current for your electrons is related to your concentration, electron concentration times your velocity. So therefore your total, of course this one can be also expressed by this one, and this VDN will be also equal to this one. So the total current drift is equal to the whole current plus the electron current. So that's a Jp drift plus Jn drift. So that's a very simple concept. The total current for sure is a combination of the electron and then the whole current, and therefore you can have mu n plus mu pp and times E here. So that just put this together. This one will become this one. And here is some typical numbers. I say from the last slide, we understand that the basic definition for the mobility is only matter with effective mass, only matter with mean free time. So that also means this is some constant number related to the material properties. So now you can see in the case of a silicon, the electron mobility is around like 1,300, but the silicon has a problem with a very low hole mobility, and that's why that we will consider to have some other material to compensate the problem of the silicon. For example, if we use gallium arsenide, so gallium arsenide is well known for the high-speed communication application, and this is because the gallium arsenide has a very high electron mobility. That's why if you look at for all the commercial product related to the communication, high-speed transport, like the cell phone inside, or even for the base station, actually there's already lots of gallium arsenide technology when we need this electronic for the communication, because the gallium arsenide is very well known for the high speed characteristic, and that's because the gallium arsenide has a very high mobility, electron mobility. And on the other hand, if you look at another very well-known material that's called the germanium, and germanium is good for the electron mobility, so that's around like 4,000. But the germanium is actually well known is for the practical application, because due to the very high hole mobility. So when we try to understand like the why, like the semiconductor device have, if you look at the very advanced technology, actually the semiconductor device is very complicated. One of the reasons for complicated is always try to solve the certain issues, because there's no material that's perfect in every aspect. For example, in the silicon, it's good, it's stable, and we have the good SiO2 as a dielectric, we have the good mobility, but we have very low hole mobility. So that's why if you look at a simple transistor as a MOSFET, so when we try to understand this equation, this is parameter behind the importance of this parameter, it's always good to link to the transistor characteristic, because in the end our goal is we have to use this basic knowledge to design our transistor to improve our transistor performance. So it's always good to link to the transistor characteristic, especially the drain current, which is the most important one for the transistor. So now we all know, in the previous slide we have been already mentioned that if we look at for the transistor, the most important characteristic for us is our drain current versus gate voltage. And in the previous example, what we actually illustrate is always use an N-MOSFET. Since the N-MOSFET is the very common use, and also the characteristic is much easy to illustrate. So in the case of the N-MOSFET, we have already mentioned that once we increase the gate bias with a certain large enough voltage, the current is increased. And this is in the case, for example, let's say if we use a silicon material here, and then the current increase under the positive gate bias. This is because we start to have the electrons. We usually call this as an inversion channel. Later on, when we talk about MOSFET, we will talk a little bit more about why we call this inversion. But at this moment, just try to accept there's a term called the inversion. So this is electron inversion in P substrate. The reason why we have to mention the P substrate here is because right now we have to also to draw the current that's for the P MOSFET. So I won't draw again for the N MOSFET, because if you look at the several slides before, in the beginning, in the introduction, every MOSFET what I'm drawing is N MOS. So that's already pretty common. But now if we look at, there's a case what we call the P MOSFET. The P MOSFET is in the case that we fabricate our MOSFET in the N-type substrate. So that's why in here I mentioned this is P-type, because that's a completely opposite compared to our N-MOS. And in the P MOSFET, this is fabricated on the N substrate. We still have the source and drain, but right now we dope the P plus for our source and drain. So if you try to compare to the N MOS, is we dope the N plus for the source and drain, but right now we dope the P plus. And the rest of the structure are the same. We still have the dielectric. And we still have the gate metal. So now you can see the basic idea for this P MOSFET. The basic structure for this P MOSFET is exactly the same like an N MOSFET. The only change is substrate doping. The only change is our doping in the source drain. And because we change the substrate doping, we change the source drain region, that actually also change our bias condition. Right now, we are not applying the positive gate bias. Actually, right now we apply the negative gate bias. So that's a minus gate bias will be applied. And the reason that we apply the minus the gate bias, minus VG, this is because we want to induce the hole. So now you can see that's still very similar to the case of NMOS, but the NMOS phase we apply the positive gate bias, we start to attract the electrons in the channel. In the case of PMOS phase, we apply the negative gate bias. Now we attract the holes in the channel here. And still the same, the rest of the detailed operation we won't talk about in here. But the concept still the same. The drain current in the P MOSFET still proportional to our hole mobility. So the drain current in the MOSFET is proportional to our electron mobility, and then the drain current in the P MOSFET is proportional to our whole mobility here. So therefore, how this defines operation? In the beginning, as I say, we apply negative gate bias. So we're starting from 0 to negative. Once you have a negative enough, so you start to attract the holes. You start to generate the positive charges in the channel. So therefore, you still start to have the current. So that's a typical, like an IDVG for the P MOSFET. And this is in the case of silicon. But now you see, we have a symmetric, like an IV curve. So that means the current in the NMOS and then the current in the PMOS is not equal. And this is because in the P MOSFET, we have very low hole mobility. This is only 400. And this is 1,300. So that means that the current conducting by the holes will be only 1/3 compared to the current conducting by the electrons here. And for the engineer, for the every engineering scenes or natural scenes, we always prefer to have the symmetric in terms of most of the, like the general rule that we want to have a symmetric. Of course, for the real understanding, there's definitely the reason that we still hope to have the symmetric current for the electron and holes. This is because due to the performance requirement. But in general, we definitely hope this current can be as higher as a silicon. So that's why we have to use this germanium, because germanium has a similar or even slightly larger hole mobility compared to electron. So ideally, if we use a germanium as a material to fabricate the P MOSFET, then we can have the current should be roughly like the same one like in the N MOSFET. So that's a germanium. So that's a seems why we are very caring about the mobility, because the mobility, it actually in the end will influence our current. The current in the end will influence the performance of our electronics. So in the case of silicon, we have the very low hole mobility. So therefore, we have a very low the hole current. So that's why we prefer to use the germanium. This is because the germanium has a good hole mobility, and that can give us the advantage that we fabricate the P MOSFET that has the same output current just like the N MOSFET here. So that's just one additional try to write down here. So P MOSFET is basically operating by consider we have the hole inversion in N substrate. So this is hole inversion in the N substrate, and this is electron inversion in the P substrate. So that's the difference between the NMOS and PMOS. And of course, later when we talk about the MOSFET, we will talk about this again. But now I believe with the time we talk about MOSFET, you should already familiar with this. Okay, so we will take a break for 10 minutes and we'll come back later. Today we have homework, so you can put your homework here. 这个的话其实应该是，那你们这个就是，我画上。对，厂商，因为它是，对，因为这都永远都是从电子，它其实这边也是从电子套这边来，电子套这边来，所以这边才会留下来电动。对，它都是电子，对，电子往上讲，然后这边是电子，对，讲的都是电子，谢谢。这个好问题耶。其实这种情况下的话，ED 应该还是会在这边，对，在靠近，因为这个是 N 派，所以 ED 还是会靠近。
可是 EF 在它以上的话，就几乎就是会有电子，会有 ED 会在 EF 的上面。
没有 ，EF 它的意思其实是只是说，它就表示说你的这个 energy level 它是跟你的 concentration 有关系。原本你的 EF 只是一个 distribution， 对，而且这个时候考量的是不是原本我们讲 ED 是把你原本那个额外掺杂的那个能接放进去，这个 band 带会考虑进去。但掺杂之后，你还是整个系统它还是改变你的 EF。对啊，因为你原本 EF 在这边，原本 EF 在中间嘛，然后你有个 ED 放进去之后，你现在不知道 ED 会多少，但是它 general 会让你 EF 往上去，所以它其实是我只能说，我觉得它是用两种概念把它混在一起，然后最终你就会有一个 EF 会靠近 EC， 因为它就变成比较靠近那个 N type 的。对，
所以也不太能确定说 ED 就是大概现在哪个。
我只能说你的，例如说 EF 越靠近 EC， 就代表你的 ED 是越像 N type。对，因为它这个是 ED 只有本身考虑你额外掺杂那个 energy level， 但你掺杂完之后 ionize 完之后，你让整个系统的 EF 改变。对。
我只知道说就是 freeze out 就是 EK 的时候，
对，
它的 EF 会夹在 EC 跟 ED 的中间，就是
EF 夹在 EC， OK，
就是它温度升高，我就有点不太知道它大概的那个相对关系就是做在。
我觉得这可能要查一下，看看有没有就是实际的 equation。对，就是有实际可以去算出来说 ED 跟 EF，ED EF 的关系。对。 Okay, so the drift current is just the summation of the whole current density, and then plus the electron current density. So the current density J is a charge per second crossing unit area plane to normal direction of the current flow. So that's just a current density. And based on the previous slides, we know that the whole current density can be expressed as this one, and electron density can be expressed as this one. So the total drift current is equal to Jn drift plus Jp drift, and that will be equal to Q mu n plus Q mu p p e, and we also define this term as a conductivity. So this one we define as a conductivity. Sigma here. So that is equal to sigma E. And one thing is also want to mention that the conductivity is just the 1 over conductivity is resistivity. So resistivity is equal to 1 over sigma, show me here. So this is slide is a summary. So the total current has to consider the electron drift current plus the whole drift current, and also we define sigma as conductivity, and the resistivity is 1 over sigma. And here is a sum like the concentration dependence of the conductivity here. So I think it's very straightforward that as long as you have the higher concentration, your conductivity is lower. So I think that this is pretty like the common sense. But now we have the very quite nice proof by using this equation. Also tell us that as long as we have the higher concentration, it always has a lower higher concentration here, higher conductivity, and lower resistivity here. And one thing is also we can link to this knowledge on our device, try to understand that why we have to design our device with N plus, with a high concentration in the source drain region. So again, if you look at the structure of the MOSFET here, so we have already know that the source drain usually we try to dope as a high concentration region, for example, the N++. But that's a reason, it must have a reason. So everything, when we try to design this our device, it must come on with some certain, like the theory, certain equation, certain purpose here. And we can also use this very simple conductivity or resistivity equation to understand why we have to design this with N++. But then we have to also, before we talk about the reason, we have to understand that if you consider the carrier, we all know this is the MOSFET structure, so we have a dielectric here. And on top of dielectric, we have the metal here. So once we consider the carrier, for example, electron transport from here to here, move to the right, and then to the out. This is, for example, the electron current, and each region has a different resistance. So the resistance network for this MOSFET is shown here. First of all, we have the contact resistance, because you put the metal on top of your semiconductor. These are the two different materials, so they must have the contact resistance in between. And later, with this source region, we have also a source resistance. And then in the channel region, we also have the channel resistance here. And again, in the drain region, we have the drain resistance. Then in this contact region, we have the contact resistance here. So now, we will consider the total resistance from left to the right. That's equal to 2RC plus channel resistance plus source drain resistance, right? So that's a very simple case from the left to right. That's very easy to be understood. This is very simple resistance network, but actually this resistance network is very useful. Like if you once you start doing the research, you try to analyze the resistance, no matter what kind of the device you are working on, the resistance network in the channel from the contact source drain to the channel is roughly more or less the same, like in this one. And therefore, of course, we all know the purpose is always try to have the high current. The current is always related to performance. So as long as we can fabricate the device with a high current, that's a certain indicator that our device has a good performance. If we want to have a high current, that means we need to have a low resistance. So when we design the transistor, the goal is trying to reduce the resistance here. And if we try to reduce resistance, of course, it would be good that every term can be reduced. But if we want to reduce every term, there's a different strategy for each one. For example, we have to optimize the contact resistance. So if you start to working on fabrication measurement of your own device, you can realize that why the RC is very important. So the RC is a kind of like the directly linked to the current. If you have a low RC, so you have a very high current. That's the purpose. So for sure, if we can reduce RC, that would be perfect. Or we can reduce the channel resistance. The channel resistance is mainly related to our mobility. So that's why the mobility is important. That if we can, it's related to 1 over mobility, related to 1 over mobility. So that means if we have a higher mobility, then we have a lower resistance. That's also good for us. But now we're talking about the source drain, because if we can use N++, so based on this graph, N++ is in where? N++ is somewhere in here. The double plus means it's a very high concentration, probably in the order of the 10 to 20 or even beyond. And in the order of 10 to 20 give us a lower resistance here. So that's why one of the strategy try to reduce the total resistance is we need to have the very high concentration of the source drain, because if we have a high concentration of source drain, we can reduce the resistance here, and once reduce resistance here, the total resistance is reduced and our current is increased. So that's actually our strategy to design the transistor. We always try to design the very high concentration in the source drain because we want to reduce the resistance. Okay, so that's the concept related to the conductivity or resistivity or related to the drift current. And next is that the semiconductor material is not perfect. There's always lots of the imperfections inside. It can be the defect, it can be the vacancy, it can be the anything. So these imperfections can cause certain collision or scattering inside, and there are the two main mechanisms. First one is what we call the phonon scattering. And the second one is we call the ionized impurity scattering, or we call the Coulomb scattering. So then next one we start to talk about what is the phonon scattering. So phonons are the particle representation of the vibration of the atoms. So once you start to see the atom vibration, you will start to see the phonons. So that's a vibration of the atoms. Vibration atoms in the crystal, the sort of a vibration that carries sound. So that's why we call this as a phonon, 声子. So in the term with a phonon, similar to the one with the phonon, there's a term called the photon. That's a 光子. So phonon is called the 声子 because it's once you have a vibration of atoms, that's similar to the vibration that carries sound. So that's why we call this as a phonon. So since this is related to the vibration of the atom, so it must also correlate with the temperature. So phonon scattering mobility decrease when temperature rise. This is because once you have the high temperature, actually your vibration become larger here. So the mobility phonon can be calculated as shown here. In here, just show the conclusion, which is in proportional to the temperature like this. So that's a phonon scattering. On the other hand, there's one that we call the Coulomb scattering. This is one much easily to be understood because this is related to the Coulomb force here. So if right now you have one certain, for example, like the particle or charge, which is electrons charges here, and right now if you have the one electrons want to move towards the right, and for sure that you have the two negative charge, and that will create the repulsive Coulomb force. So that means this negative charge will change the moving direction of these electrons. So therefore, this will become like this way. So that's scattering. That's what we call the Coulomb scattering. On the other hand, there's also the possibility that you will have the one particle here, but that's a positive charge. But now you have one electron move towards the right, and of course, due to this positive charge, and you will have the attractive Coulomb force. So that's a very simple physics. So it's mainly related to the Coulomb force here. So in this case, this will influence our mobility. So that's why we call the Coulomb scattering. So electron can be scattered by acceptor ion or donor ion, and the same is true for hole here. So the mobility here is this mechanism is also the temperature dependent. So therefore, you have this kind of the temperature correlation. So in sum, if we consider the temperature dependency of the electron mobility in silicon with a different temperature, basically you will see this kind of curve. When the low temperature, high temperature, you actually induce a different mechanism here. At the low temperature, it's mainly influenced by the impurity scattering, and in the high temperature, it's mainly influenced by the lattice scattering. So that's a phonon scattering. So that's a phonon scattering. So that's a general, like the scattering mechanism in the silicon. So therefore, the total scattering rate is shown here is determined by sum of the inverse of each term here, and therefore the mobility is also determined by the sum of this inverse, as shown here. And when we talk about the carrier transport, we also need to consider that ideally it's like we apply electric field, our carrier should be linear proportion to our electric field. That means as larger as we apply the voltage, as larger as we apply the electric field, the velocity should be go faster as we expected. And because we think that's a linear proportion. But the problem is, this is not true because there's a velocity saturation. So in the low field region, we expect that we increase the electric field, our carrier can transport faster with a linear proportional. But right now, if we go to the very high electric field and start, we will see this one is what we call the velocity saturation. And this is when we consider the very high electric field. Therefore, we need to consider, we need to try to, if you expand your device is going to operate in the very high electric field, and therefore you need to certainly find out that the velocity saturation in the high electric field is good or not. For example, we have already mentioned the gallium arsenide. This is one with a very high mobility. That's why people prefer to use for example, mobile communication, high-speed communication. But this only true in the case with the low field. In the certain case of high field, you can see the gallium arsenide shows a decrease of the velocity saturation. That means this material probably not suitable in the case that we want the carrier can be transported very fast, but at the meantime, this carrier will be biased with a large electric field. And what will be the scenario that we want the carrier can be transported very fast, but at the meantime, this system will also be biased in the large bias. And this is a case usually happen in the base station. So you know what's a base station. Base station is the one in the ground. You will generate very high power to pulse your signal. That's why your cell phone has a signal for 4G, 5G. And if you go to some countryside, some mountain region, some remote area, you probably have a very poor signal, very low signal. That's because in those regions, there's no base station, or the signal for the base station is not strong enough. And how do we create a strong signal for the base station? We need to have a device that can operate in the very high power condition. But in the meantime, the power condition, for sure this device, the base station, the system inside base station need to be operated in a high power condition, but also with a high speed probability, because that's for the communication. So usually we need the system like the RF power amplifier. So as you know, RF is mainly related to radio frequency. So that's the case we use for the high frequency communication, but also we need to have the power amplifier, this kind of function. The power amplifier, that means we want this system can sustain the very high power, can amplify the power to boost the power. And usually this device need to be operating in the very high bias and then the high current condition, because the power is equal to the current times the voltage, the current times the voltage, or and then that means that if we want to have the perfect RF power amplifier, first of all, the material, the device need to be operating in the high speed. And second, the device will be operating in the high power condition. Therefore, in this case, we have to consider the velocity saturation, because our device will be operating in certain this region with a high bias. But in the meantime, we also want to have the high frequency, high velocity. So it will be good to have a certain material that shows linear, but also very good velocity saturation. And there's a certain material like this one. This is, for example, like a gallium nitride. So gallium nitride is a good material for the power amplifier in the RF application. This is the reason is because they have the higher velocity saturation here. So it must be actually everything has a reason for some application. Why the gallium arsenide can be only used for the cell phone, not for the base station. Why the gallium nitride is perfect for the base station. In the end, it's all comes from the fundamental device property, fundamental physics, fundamental material properties. Okay, So finally, we finished the discussion related to carrier drift. So the carrier drift is mainly related to you apply the bias and then your carrier start to move based on your bias. But in reality, we also have to consider another mechanism that we call the carrier diffusion. So diffusion is from the chemistry. You already know the diffusion process. Diffusion is very like common sense, straightforward phenomenon. So diffusion is a process whereby particles flow from region of the high concentration toward the region of a low concentration. For example, if in this region you have a high concentration of a carrier, and for sure, this carrier will like to move to the right because this is empty. Everyone wants to move to the place where it has less people, less crowded. So this is a region that has less people, less crowded. So that's a diffusion. So if you try to plot, we have the electron concentration and because if we have an electron concentration distribution in this way, so that means in this region we have a high electron concentration. In this region we have a low electron concentration. So this is x-axis, and therefore, because we have a high electron concentration in this region, this electron will try to move towards the left. So therefore, we have the electron flux towards the left. And that creates the electron diffusion current because the current is in the opposite of the electrons. So therefore, the electron diffusion current is in this direction. So similar, if you look at the case for the hole, so we have the whole concentration. And again, we assume our whole concentration profile is like here. So that means we have the whole, so this is a region where have the high hole concentration. This is region has the low hole concentration. So that means we have the whole flux toward the left. And then the current direction is the same like the whole current direction. So therefore, your whole current diffusion is in this direction. Right? So now, how do we estimate the diffusion current? So the Jn electron diffusion current is equal to Q dN concentration gradient dN dx, right? So this is our concentration gradient, and this term is diffusion coefficient. this is diffusion coefficient because the current right now is to the right, so that's just like this one. But if you now look at the case of the Hall diffusion, that's equal to, again, the same Q dP Hall concentration gradient. So that's a dP over dx. But the problem is now the Hall is flowing towards the negative direction because this is the same like this. So we have to consider there's a negative sign here because right now the whole current flow toward the current flow toward the negative x axis. So that's why we have the negative sign here. So I believe the concept for the diffusion is very simple to understand compared to the last week. We talked about all the Fermi energy, all the probability distribution, all the equation to calculate the concentration. I think the understanding for the carrier transport in terms of drift and diffusion, that's much simple. Okay, so now it's almost get close to the end that for the final that our goal is want to understand the total current. So for sure, the total current is a combination of electron current plus a Hall current. But now the electron current has two parts. First is a drift. So the contribution comes from the drift current plus the contribution comes from the diffusion current. And the same thing is true for the Hall current. So that's a JP drift plus JP diffusion. And now we just put everything what we already know in the previous one together here. So we have a Q N nu N E plus Q dN over dx, and this is a Q P mu PE minus Q dP dP dx here. So that's all. So therefore the current right now is mainly matter with your electric field, mobility, concentration gradient, electric field, mobility, concentration gradient. And of course, it's also correlated with your concentration and diffusion coefficient. So in the end, all these parameters influence the total current in the one piece of the semiconductor material. Okay, so, but in reality, not everything is as simple as we shown that we have the very uniform distribution. So in reality, it is possible that the semiconductor has a non-uniform doped with a donor impurity, altered. So this is the case. So now I believe everyone can understand this Venn diagram, but the Venn diagram is not the one. The concept is same, just it's not flat. And if you look at this one, this is Fermi energy. So Fermi energy in here is close to a conduction band. In here is far away from your conduction band. So what does that mean? This means if you try to plot the electron concentration, if you try to plot the electron concentration, we expect to see your concentration profile is like here, because this region you have an EF close to EC, so you have a higher concentration. This region your EF is slightly far away from EC, you have a low concentration, so we have a non-uniform distribution here. Of course, based on all the things we have, we already have this equation, and we can also define the concentration distribution. In the end, we can have this one. This is electric field, and that's correlate with your concentration distribution with respect to the x-axis. So finally, there's a way try to find the correlation between the diffusion coefficient versus the mobility. So in the case of the angular equilibrium, so in the case of the equilibrium case, this current is equal to 0. So now we all know the left hand side is a drift and right hand side is a diffusion. And because this equal to 0, and we also know this, so in the end you can have this equation, and therefore we have the relationship called the Einstein relationship is dN and dP. So we have the way to calculate the mobility and diffusion coefficient by using the Einstein relationship here. So here is some numbers, mu1, mu-p, dN, dP. So that's just for your information. Okay, so that's a summary. We have introduced two basic transport mechanisms are drift, because due to the applied electric field, or diffusion due to there's a concentration gradient here. And here is all the equation we have been mentioned. And of course, I think the most important one is this one, this one, and this one, this one. You don't have to derive everything by yourself, but at least you need to understand how this equation coming, what's the physics mechanism behind, because that can give us a little bit more about the physics sense in the future once you analyze the semiconductor device. So you will realize that there's a problem of the electric field will induce a current. There's also the the problem that if there's a concentration not uniform, that can also create the certain of the current as well. Okay, so today we have the little bit short class because I think we have already explained a lot of things, so you need to find the time for the digest. So we will stop the class today, and from next week we'll move to the non-equilibrium case. So far what we are dealing with, everything is in equilibrium. There's no additional issues, but now we finish the equilibrium. Next week we'll start to consider case of the non-equilibrium case. And also just please submit your homework here, and see you guys next week.